Hello guys, welcome to the new video. Today we are going to learn metallic character, non-metallic character and chemical reactivity. But before I begin with that, I just wanted to share something with you, that is the typical elements and how to determine the period and the group of an element that might be given to you, that might not be given to you. So how to determine that? To determine that, you must know how many shells are present and what is the valence electron present. Suppose I give the element as 2, 8, 7. So here total number of shells present is 3. So this indicates that it will belong to the third period. But there are 7 valence electrons. So valence electron is 7, indicating that it is located in 10 plus 7 group. That is 17 group. Now why are we adding this 10? This 10 is just added for convenience. Whenever there is greater than 2 electrons in the valence shell, transition metals we are not having right now. So whenever there is greater than 2, omitting the transition metals for now, later on we will include that, not now. So whenever it exceeds 2 electrons valence, then add 10 to it. Otherwise, suppose it is 2, 8, 1. Then if you add up 10 with 1, then it becomes 11, but sodium is not in group 11, it is in group 1. So in that case, write this only as the group number 1. But whenever it is exceeding, add 10 to it and then write the group number. So this becomes 17th group and third period. So period number is determined by the number of shells, while group number is determined how many valence electrons are present in the valence shell. This is the basic thing of how to determine the period and group number. Now the next thing is typical elements. Typical elements. Typical elements is basically the group 3 elements. Sorry, not group 3, period 3 elements. It's the period 3 elements. The period 3 elements, they are called typical elements. What are the period 3 elements? Na, Mg, Al, Si, P, S, Cl, Ar. These are the group period 3 elements. And this summarize the properties of their respective groups. Okay, their respective group properties will be summarized by Na, Mg, Al, Si, P, S, L, Ar. So for this reason, group 3 are called typical elements. Now it is not group 2 because of some internal property that is called oxidation state number. These have fixed oxidation state number, but group 2 varies. So we have considered group 3 as the typical elements. Okay. Now let us get into the next periodic property, that is known as metallic character. So by the term itself, we have understood that metallic character is somehow related, to losing electron to form positive charge. Because metals cannot give electron, metals have to lose electron. So metals will lose electron to form positive charge. Let us say this is sodium metal. So sodium metal loses 1 electron to form sodium positive. Magnesium loses 2 electrons to form magnesium dipositive. So this is the basic. Now in this basic, what changes are observed? Na, Na plus, Mg, Mg2 plus. What is the change? Na and Mg, they are not same group but same periods. So Na, it has got 11 protons, 10 electrons, Na positive, and this has got 12 protons and now it has got 10 electrons. They are isoelectronic species, so both of them have the same power. So this was done in the isoelectronic species as well. 10 electron attracting 12, 10 electron attracting 11. Whose size will be greater? First of all, you have to think that Na's size is less than Mg's size. That is one factor. Another factor is charge factor. So 10 can pull 12 more or 10 can pull 11 more. Write the answer in the comments. Okay? Okay. So metallic character will decrease across a group. Why? Because metal What is the property of metal? To lose electron. But you check as you proceed, Na find it loses electrons, Mg find it loses electrons, Al find it loses electrons. Silicon, does it lose electron? Very rare case. Silicon is sharing electrons. It does not lose readily. Okay. After silicon, phosphorus. Never have I seen phosphorus losing electrons at least. It gains electrons, but it can lose electron. Again, it's a rare case. Next is sulfur. Next is chlorine. And last one is argon, which I am not writing because argon is a noble gas. Okay. So you see, this is a metal. This is again a metalloid. This is a non-metal. This is also a non-metal. This is also a non-metal. So gradual transition of metal to non-metal. So metallic character decreases. Why it decreases? What is the chemical reason for decreasing? Its simple reason is nuclear pool increases. So with increasing nuclear pool, atomic size has to decrease. And what was the factor of nuclear pool? You increase the nuclear pool, then the electrons will be more closely attracted. So if this attracts the electron more closer, then it is very much difficult to remove that electron out. So as a result, it will tend to gain electrons more easily, not lose the electrons easily. So that is where metallic character decreases across a period. Next is down a group. Down a group, metallic character is always deemed to increase. How? Again, the same dominant factor of atomic size. Atomic size increases. Outer electrons are shielded by the inner orbitals. So as a result, it can easily be knocked off. So that is why metallic character increases. So the most metallic element is CS, right? Because this side will decrease. So the most metallic element is CS. It is located below cesium. Okay. Now let's move on to the reverse of this. What is the reverse of this? Non-metallic character. Now if metallic character will decrease, the non-metallic character has to increase. The logic remains same. That is, nuclear pool will increase, electrons are more closely attracted, cannot be knocked off easily. But since, suppose, let me give a reason. This is suppose this is a force producer. Let us say force is being produced from here. So suppose this is, let us say it is a magnetic force. So magnetic. So you keep a magnetic something that will get attracted. Let's say iron. So something of made of iron is kept here, and its range is still here. Okay. All sides. So will this not get attracted to this? It will get attracted to this. Same concept applies in nucleus. If the nucleus is attracting or binding the electrons more closer, and you bring another electron closer to it, this nucleus can attract that also. So it can easily pull in the electron. So that is where the non-metallic character applies. Okay. So non-metallic characters reason is this. That is, the electrons are more closely bounded. So as a result, any other electron being added to it can be easily attracted to it by it. And down a group, non-metallic character has to decrease. Non-metallic character has to decrease because no property can increase both in the period and group. So if it is increasing in the constant period, it has to decrease in the group. What is the logic? Atomic size. So as it is atomic size is increasing, its tendency to lose electrons will increase. Now you will say, why? Cl minus can never form Cl plus, can it? It cannot form. But Cl, if size is small, Cl size is greater, atomic size increases down the group. So Cl's, this R is greater than fluorine's R, obviously it is greater, and we have learned that atomic size is the dominant factor. So thinking of that shielding effect, fluorine, the energy that will be needed to throw that electron is comparatively lesser in case of fluorine. So it will be throwing up easily, comparatively. We are not saying that it has to get converted to cation, no. But its metallic character increases somehow, very little but increasing. This non-metallic character decreasing. That is the main. Like if you see iodine, it has got a very huge size, so it can easily knock off the electron. Now I am not saying as easily as the first metal, like as a group 1 element. I am not saying that. But as compared to the top elements, it can easily be removed. That is what I am saying. Okay, so this was non-metallic character. Now, oxidation and reduction. A little bit of oxidation reduction will induce over here. That is, if sodium metal, let's take sodium, loses electron to form Na positive, and Cl, it will gain electron to form Cl negative. Right? So this is something. Now this is undergoing oxidation, this is undergoing reduction. So this is undergoing this is undergoing reduction. So what can you understand? Something that undergoes oxidation and reduces the other substance is called reducing agent. Itself undergoing oxidation, but reducing someone else is reducing agent. So metals undergo oxidation. So what will it do to the neighboring? Oxidize. Sorry, reduce. It is undergoing oxidation, so it will reduce the byproduct. Let us take NaCl. So NaCl, whenever it is not like this, right? Na plus Cl 2 forms NaCl. So we can write 2 NaCl, balancing I'm doing this. Okay, so Na has come over here. So Na has oxidized or decreased? Obviously it has oxidized because it was initially in the state 0, now it is in the state plus 1. So it has increased, so it is oxidation. But this is reduction because this was 0 and now this is minus 1. So this has got decreased, so this is reduction. Now this is undergoing oxidation and it is simultaneously reducing this person also. So this is acting as a reducing agent. This is undergoing oxidation, reduction, sorry, and this is oxidizing this person. So this is acting as a reducing agent. So what can you conclude from here? Metals are good reducing agents. So reducing power decreases across a period. Why? Because ultimately when you come to chlorine, it will become an oxidizing agent. Ultimately you come to chlorine, it will become an oxidizing agent. So metallic character decreases across a period, reducing power also decreases across a period. And we can say the reverse also, that is the reducing power increases down a group. Okay? And in terms of non-metallic character, we can say oxidizing power increases across a period. Because this will do the less oxidizing power, this is having the most oxidizing power. Oxidizing agent and reducing agent, just two main things, and oxidation reduction. Whoever will undergo reduction, it will be oxidizing agent. Whoever undergo oxidation, that will be the reducing agent, opposite. So that is the thing, that is reducing power will decrease across a period, ultimately end up at oxidizing power, and oxidizing power will increase across a period. Starting with reducing power, it will increase with oxidizing power. Now, periodic table, left stream, left side, there are metals. So metals generally form what type of oxide? Basic oxide. Generally I am talking about, not the exception. So it's general, it will form basic oxide. So basic oxide character will decrease across a period. Why? Because let us take Na2O, that is the basic oxide, and let us come to chlorine, that is Cl2O7. Okay, this and this is completely acidic oxide, cannot be a basic oxide. This is an acidic oxide, while this is a basic oxide. For example, let's take it between something N2O5. N2O5 is an acidic oxide. You already know the reaction, that is N2O5 when reacts with water will give you HNO3. So this is the thing. So it gives you HNO3. HNO is an acid. So this is an acid anhydride of this. So that means this is an acidic oxide. So this is an acidic oxide. So ultimately you are finally ending up an acidic oxide. This is maybe slightly or feebly acidic, but it is an acidic oxide. Feebly acidic, you can say that. But this is indeed an acidic oxide. So it ends up an acidic, and starts with basic. So we can say that change is decreases. Okay, and across a period, down a group, it has to increase. So basic character increases down a group and decreases across a period. It has to increase because metallic character increases. So basic character has to increase. Same thing will happen in case of acidic oxides, okay? But we are having only the term. Generally the question comes is this side, okay? Group is very rarely asked. Okay, now the most ionic compound. The most ionic compound. What is the most ionic compound? Most ionic compound, for ionic compound you see electronegativity difference, that is there in chemical bonding only. Electronegativity difference has to be high. So whose electronegativity difference is very high? That electronegativity we have not studied yet. But I am just giving a brief, that is electronegativity will decrease down a group. Simple thing. So first group, CS is at the bottom, and last group, ignoring the noble gas, because noble gas have zero electronegativity. They have already fulfilled. Chlorine is the target. So this will combine with this. So what is that? CSF2. Okay, CSF2, it is going to have be the maximum ionic character. Okay, but this is there moreover in chemical bonding. After you study electronegativity, you will understand this more better. Okay, so then CSF2, CSF, more or less same, but we write CSF2 nomenclature rules. Okay, next is chemical reactivity. Chemical reactivity. Now, chemical reactivity is basically how much easily the valence electron can be knocked off. That is chemical reactivity. So, it is depending on the valence electron. That is why the chemical reactivity is said to be the valence electron. It is always valence electron. That is why you will find fluorine is the most chemically reactive non-metal. Then it will decrease down the group. Why? Because fluorine has got the least EF. It can release the electrons easily. Now, exception here, remember, that is F will be there. This was supposed to be, but this is not. What is this? This is electron affinity. Again, this is not come here. This is electron affinity. So basically, electron affinity of fluorine is less than taurine. So if it is less than taurine, then it can easily knock up the electron. It can easily gain an electron. So if it can easily gain an electron, then it is more reactive chemically. So fluorine is more reactive than taurine chemically. So fluorine is the most reactive. Fluorine, then chlorine, bromine, iodine, whatever it is decreasing down the group. Only for non-metals. For metals, it is not the case. For metals, it will increase down the group. For metals, it is going to increase. But for non-metals, it is the opposite. So the most reactive metal is present below, but most reactive non-metal present here. That is fluorine. Why? Present is here. That is electron affinity. Electron affinity, that is not there right now. So this is what important thing, that is for non-metals the most reactive non-metal is above the top, not below. But for metals it has to be below, cannot be the top, because chemical reactivity increases down a group. That is an important factor that is to be remembered from chemical reactivity. Now often questions come where it is neither from a group nor from a period. In that case, what is to be done? If it is not from the same group, not from the same period, like one question was there, like it was somewhat like sodium was there, calcium was there, then zinc was there, lead was there. This question was there. It was told to arrange in increasing order of chemical reactivity. Increasing order of chemical reactivity. Then how will you arrange it? Because it is not in the same group. Sodium, calcium is not in the same group. Zinc, lead is transition metal, cannot be in the same group. There is no transition metal, but zinc is also no transition metal, but located in the transition block, that is D block. Okay, anyway. So increasing order of chemical reactivity. Now why or how can we arrange this? Because they are not in the same group. Why? Check, sodium is 2,8,1, group 1. This is 2,8,8,2. Period is only different. This is zinc, this is atomic number 30, and lead is atomic number somehow 80 or 82. Maybe it is very high, so it is not there. So these are all of different periods. So we cannot. How to arrange? There was a series, if you remember, called metal activity series. In that case, you will have to take the help of metal activity series, because that tells about the reactivity of metals. So in that case, how will you arrange this? So in that case, see the metal activity series. I will not see in the exam definitely. So it is Na at the top. Some places you will find calcium written below. Calcium written below calcium written below sodium, and sodium written below calcium. Different pattern. Why? Because that is one for your reaction, that is electrochemical series, and another one is metal activity series. In metal activity series, generally sodium is placed above calcium. Okay, now it varies from book to book. Standard electron potentials are different, so somehow it happens. Okay, but generally it is like this. So after Ca, Zn, Pb. This is the basic reaction. So this is the order. So how will you arrange the order? Least is Pb. So it is Pb, Zn, then Ca, then Na. Okay, there is a debate going on between Ca and Na. Ca also comes first sometimes, Na also comes faster. But here let us consider that Na is before Ca. Okay, because we find many things are different, like when it reacts with hot water, steam water, cold water. somewhere it is different. Okay, so this is the thing. So metal activity series is to be considered when there is no group and when there is no proper thing you can what extract from the question. So in that case, use the metal activity series. But if you get the same group, then no question of coming. Like if I say, like if I give is F Cl I Br. So in that case, you don't need a periodic table electrochemical series or metal activity series. Definitely metal activity series is metal, and you cannot even apply over here. Okay. So here this is very easy. This one is very easy. So increasing means smallest, starting with smallest, and ending up with the largest. So this is the thing. Now if it is given sodium, and it is given lithium, and it is given Rb, and it is given K, and it is given CS. In that case, what will you do? So least reactive is above, located above. So lithium is the least reactive, followed by sodium, followed by potassium, followed by rubidium, followed by cesium. So this is how you have to solve the question. So this is all in today's video. We have learnt about metallic character, we have learnt about non-metallic character, we have learnt about chemical reactivity, we have learnt how to find period and group number, we have learnt in brief about typical elements. In the next video, we will be discussing about electron enthalpy, that is electron gain enthalpy or electron affinity, ionization potential, and if possible then electronegativity also. Electronegativity has got a very vast application, so we will try to make it as brief as possible. Okay, so see you in the next video.